Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 1.7 on linear independence. I'll give you steps that you can follow to determine if a set of vectors is linearly independent or linearly dependent and walk through lots of example problems. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's start by understanding how two vectors can be linearly independent or linearly dependent. Our first example is an example of two vectors that are linearly independent. Notice that v1 and v2 do not point in the same or opposite direction, and that v2, because it points in a different direction than v1, cannot be written as a multiple of v1. Our second example is an example with two vectors that are linearly dependent. Notice that v1 and v2 point in the same direction and that we can write v2 as 2 times v1, so v2 is a multiple of v1. Two vectors will be linearly independent if neither of them can be written as a scalar multiple of the other. We can also say that two vectors are linearly dependent if one vector can be expressed as a scalar multiple of the other. In example 2 above, v2 was equal to 2 times v1. We can also write this as 2v1 minus v2 is equal to the 0 vector. This equation is of the form c1v1 plus c2v2 is equal to 0. One solution to this equation is c1 is equal to 0 and c2 is equal to 0, and we call this the trivial solution. This equation will always have the trivial solution. We can also have other solutions to this equation depending on what our vectors v1 and v2 look like, and those solutions will be c1 is not equal to 0 and c2 is not equal to 0. With our vectors from example 2, we had a solution c1 is equal to 2 and c2 is equal to minus 1. Because we had this solution that was not the trivial solution, v1 and v2 were linearly dependent. Let's now learn how to determine if a set of more than two vectors is linearly independent or linearly dependent. A set of vectors v1 all the way up through vp in Rn is linearly independent if the equation x1v1 plus x2v2 all the way up through xpvp is equal to 0 has only the trivial solution. If there is a solution other than the trivial solution, the set will be linearly dependent. Let's see how this works in practice. If we want to determine if a set of vectors is linearly independent or linearly dependent, we need to start with this equation. I would suggest that you memorize this equation. This equation will either have one solution, which is the trivial solution, or it will have infinitely many solutions. Those solutions will be the trivial solution and infinitely many others. In example 2 on the previous page, when we had two dependent vectors, v1 and v2, we saw that in the equation c1v1 plus c2v2 is equal to 0, we had c1 was equal to 2 and c2 was equal to minus 1. We also could have had multiples of these. For instance, we could have had c1 is equal to 4 and c2 was equal to negative 2. That's because we have a 0 on the right-hand side. Because of this, when we have a solution other than just the trivial solution, we will get infinitely many other solutions. When we're given a set of vectors and we want to determine if they're linearly independent or linearly dependent, here's what we have to do. Our first step will be to place our set of vectors in a matrix and augment it with 0. We'll then reduce this matrix to echelon form and check for pivots. If every column has a pivot, our set of vectors will be linearly independent. And then if we have a column without a pivot, our set of vectors will be linearly dependent. To see how these vectors depend on each other, we'll have to go to step 2, and we'll have to take our augmented matrix that we already set up in step 1 and reduce it to reduced echelon form. And this will tell us exactly how the vectors depend on each other. Let's now walk through some example problems so we can see how all this works. In our first example, we're asked to determine if the vectors listed here are linearly independent. We'll label our vectors as v1, v2, and v3, and put them in a matrix augmented with 0 and reduce it to echelon form. Let's do that. We'll set up our augmented matrix. I'm not going to write down the reduction steps, but our matrix in echelon form looks like this. We'll circle our pivots and notice that every column has a pivot. Because of this, we'll get a solution, x3 is equal to 0, and then we'll get x2 is equal to 0, and then we'll get x1 is equal to 0. Remember that when every column has a pivot, we get a unique solution, and because we have 0 on our right-hand side, that solution is going to be the trivial solution. Because of this, our vectors are linearly independent. In our second example, we're not given a set of vectors, but we're given columns of a matrix, and we're asked to determine if they form a linearly independent set. If they don't, we're asked to determine how the columns depend on each other. We'll begin by labeling the columns of our matrix as v1, v2, and v3. We'll then place these vectors into a matrix augmented with 0 and reduce it to echelon form. Let's do that. We'll write down our matrix. And augment it with 0. I'm going to skip the steps again, and I'll just show you what the matrix in echelon form looks like. It looks like this. We have 1, 0, 0, 4, 1, 0, 5, 1, 0, and then 0 on our right-hand side. Let's now circle our pivots. Notice that we have a column without a pivot. Because of this, in our equation, x1v1 plus x2v2 plus x3v3 is equal to 0, x3 is a free variable and can be a value that is not 0. So because of this, we'll have solutions that are not just the trivial solution. And this tells us that the columns in our matrix are linearly dependent. To find out how the columns depend on each other, we'll take our augmented matrix and put it in reduced echelon form. I'm going to skip the steps again, and I'll just show you what our matrix in reduced echelon form looks like. It looks like this. Let's circle our pivots and then translate this augmented matrix back into algebraic form. We get x1 plus x3 is equal to 0. And then we get x2 plus x3 is equal to 0. Solving for our pivot variables, we get x1 is minus x3, and then we get x2 is also minus x3. To see the dependence relationship, let's write down our equation x1 v1 plus x2 v2 plus x3 v3 is equal to 0, and plug back in the values that we just got for x1 and x2. This gives us minus x3 v1 minus x3 v2 plus x3 v3 is equal to 0. You can see that we can cancel out our x3 terms and then get a solution for v3 that looks like this. We have v3 is equal to v1 plus v2. This tells us that our third column in our matrix is equal to the sum of our first two columns. Let's write that down because that is our dependence relationship. We can say that 5, 7, 9 is equal to 1, 2, 3 plus 4, 5, 6. For this example, you probably could have just looked at the columns and seen that V3 was V1 plus V2, but in many cases you can't do that, so I wanted to walk through this example in detail. Our third example is a little bit different than the first two because we're asked to find the value of h for which the vectors are linearly dependent. It's always a little bit harder when you have a variable in your problem. We're going to go about this the same way that we did for number 1 and number 2. We're going to label our vectors v1, v2, and v3. And we're going to place them in a matrix augmented with 0 and reduce it to echelon form. Here's where it gets a little bit different. We need the vectors to be linearly dependent, so that means we're going to have to make sure that we have at least one column without a pivot. Let's construct our augmented matrix. And we'll put this matrix in echelon form. Skipping the steps, this is what we get. Let's circle our pivots. Notice that our third column is already missing a pivot. Because of this, the vectors are linearly dependent. They will be linearly dependent for any value of h. Because of that, our answer is going to be all h. So any value of h will make the vectors linearly dependent. We're now going to go over 4 special cases where it is easy to determine if a set of vectors is linearly dependent or linearly independent. Our first special case is when we have a set of vectors that contains the 0 vector. any set of vectors that contains the 0 vector is linearly dependent. The set of vectors that I've listed here contains the 0 vector. Let's see why a set of vectors that contains the 0 vector is linearly dependent. Let's label our vectors v1 and v2 and then plug them in to our equation. We have c1 times 2, 3 plus c2 times 0, 0 is equal to our right-hand side, which is 0, 0. This equation will have a solution if c1 is equal to 0, but we don't have to have c2 equal to 0 because we have the 0 vector right there. So c2 can be any number. And because of this, we have a non-trivial solution and our set of vectors is linearly dependent. Our second special case is when we have a single non-zero vector. A set containing only one non-zero vector is always linearly independent. Let's plug our vector into our equation and see why this is. We have c1 times 2, 3 is equal to 0, 0. You can see that the only solution to this equation is going to be when c1 is equal to 0, which is the trivial solution. And when we only have the trivial solution, our set of vectors is linearly independent. Let's now look at example 3. In example 3, we have more vectors than there are entries in each vector. What we mean by that is in this set, we have 3 vectors, and we have 2 entries, or 2 components, in each vector. So we have more vectors than we have entries in each vector. Whenever this happens, our set of vectors is linearly dependent. To understand why this happens, with this example, we're going to put our vectors into an augmented matrix. Our augmented matrix is going to be v1, v2, v3, augmented with 0, and we'll go ahead and put in our vectors. We have 1, 2, 3, 4, 5, 6, and 0 on the right-hand side. When we put this matrix in echelon form, we get a matrix that looks like this. We have 2 pivots in our matrix, and we have a column without a pivot. So that means C3 is a free variable and can take on values other than 0. So we will have a non-trivial solution, and our vectors will be linearly dependent. Our last special case is when we have one vector in our set that is a multiple of another vector. Notice that in this set, our second vector is 2 times our first vector. If we label our vectors v1, v2, and v3, we can see that v2 is equal to 2 times v1. When we plug this into our equation, we get c1 v1 plus c2, and then instead of v2, we're going to plug in 2v1 plus c3 v3 is equal to 0. Let's combine the constants that multiply v1. We get c1 plus 2c2 times v1 plus c3 v3 is equal to 0. We'll have a solution to this equation if c3 is equal to 0, and then if c1 plus 2c2 is equal to 0. This equation has an infinite number of solutions. For example, we could have c1 equal to minus 4, and that would give us that c2 is equal to 2. Because we have an infinite number of solutions for C1 and C2, we don't just have the trivial solution, so this set of vectors is linearly dependent. When you're working with a set of vectors and see that it's one of these 4 special cases that we've just gone over, you don't have to do any more work, and you can just easily know if the set is linearly independent or if it's linearly dependent. Be sure to check out the next video in this series where you'll learn all about the span of a set of vectors.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.